Yeah, so I'm clearly not Andrei Bernavig. Uh, so if you were expecting him this morning, I'm sorry. He will be the next speaker. Um, this is mystery talk number 2. If you were here yesterday, I promised you a second mystery talk, so that's what this is. Please stop me and ask questions whenever you have questions, because I don't really need to get through all of this. It's really to expose you to a very new technique and the capabilities of this technique. And actually, for the theorists among this crowd, it's mainly for you to think about what one might be able to measure with such a new technique, right? Like, that's what I'd like you to think about, because as you can see from the title, it includes the words time resolved. And STM, if you're familiar with it at all, is it's a probe of equilibrium physics. The time it takes for us to take data could be anywhere from minutes to hours to days. And the time is that we take data, the time scale, is nothing close to the femtosecond or picosecond time scales on which dynamics happen in materials. So the question you have to ask yourself is, how am I going to get time resolution from such a probe? And that's the first. I'm going to try and answer this question. Hopefully you'll get an idea by the end of the talk. But more importantly, I hope you understand how the technology works and exactly what we are measuring. And I hope that will allow you to think carefully about what one could do with such a technique, like I said before. Okay, with that preamble, let me just start. Okay, so, the scanning tunneling microscope was invented in 1981 and by Binning and Rohr. For this, they got the Nobel Prize. And it was very quickly afterwards, surprisingly, within a decade, that people started thinking about how one might be able to get time resolution from a scanning tunneling microscope. So in 1991, we had the first results that combined a pulsed laser. So this is laser pulses of laser light that you shine on the tip sample junction. And then they were able to get nanosecond time resolution and, not great spatial resolution. I'm not sure exactly why. So then until 2002, which is not that, it's long ago, but it's only a decade ago. 2 decades ago. The fastest time resolution was limited to 20 picoseconds. And remember, picoseconds, the time scale of picoseconds is pretty long on the scale of dynamics, right? What kinds of things change at picosecond time scales? Usually it's collective phenomena. If you have a charge density wave and you shine light, then you can expect some excitation and then decay over picosecond time scales. Maybe some Magnon excitations, but these have to be collective modes that decay over picosecond time scales. Most dynamics, you want better time resolution than that, femtoseconds. So then in 2002, actually, so until 2002, this was the problem. The time resolution was not great. In 2002, there was a new technique invented, and this is the technique I'm going to show you, which allowed us to get into the picosecond time resolution regime. And then in 2010, there was, more refinement for better signal to noise, and that's where we are. So you might ask, why haven't you heard if 1991 was when the first attempts were made to get time resolution from STM? Why don't we have a huge number of publications using this technique? And the answer is that there were many technical hurdles that needed to be solved. One of the biggest technical problems was, you have a tip and a sample, you're shining light. Light is absorbed not just by your sample, but also by your tip, which means your tip is going to expand. And the question would be, how do you decouple the effects of this expansion of the tip from any phenomena that you're going to measure? Because what we're measuring, remember, in the end, It's SDM, so we're going to measure the current. And if the tip length changes, the current is going to change. So how do you know? How do you decouple these things? So that was one of the biggest problems people had to solve. And then there were a lot of laser-related technologies that allowed us to actually get to this point where we're actually able to use this instrument to do real research on quantum materials. So until recently, this technique has been limited to the studying molecules on surfaces or proof of concept in materials like gold, silver, gallium arsenide, niobium diselenide. And so what I hope to show you today is that it's now reached the level of maturity where you can actually get really interesting information on quantum materials. Okay. So why would you want to do this, right? There are lots of sort of terahertz techniques and so on that already measure dynamics. One reason is that STM is a local probe, and so there are questions. That the terahertz people have that they cannot find answers to because they cannot see what's going on. But we can. We can see what's going on, and we can make local measurements. And so that's very powerful. So there are a couple of really cool experiments that have been done, with shining light on superconductors. So Andrea Cavalleri's group, for example, has done a series of experiments where they show that if you shine pulse laser light on a superconductor, then you can, or even in a material that's non-superconducting sometimes, in any case, you can increase the transition temperature of the superconductor by quite a bit, sometimes even 100%. But the thing is, the way they're measuring, they see a gap being formed, but they don't exactly know whether it's a superconducting gap or not. It's really hard to do transport measurements on such time scales. So if we could actually go in and look at spectroscopy over these time scales, we could really find answers to this question: are we really getting enhanced superconductivity because of light? And there are many other phases you can realize. One interesting thing about light is that circularly polarized light breaks time reversal symmetry. So you can use it to break time reversal symmetry in a material externally without applying a magnetic field. So that then you can imagine having a Dirac cone like this, applying circularly polarized light, gapping out the Dirac cone, and then realizing edge states. Okay? So those are very cool uses of light. So what can one do with an ultrafast STM? It opens a new window into quantum materials, like I said. We can measure spin phonon excitations. It's actually something that might be extremely useful for quantum information, right? In quantum information, when you have solid-state-based qubits that you're trying to realize, many of these qubits are little molecules or atoms or die vacancies in diamond, for example. And if you could go in and shine light and look at the excited state and the ground state of such a system, then you could get information on what determines the lifetime of your qubit, for example. You can create and measure transient metastable phases, like, for example, light-induced superconductivity, high-temperature superconductivity, or you can induce new types of order. I already told you can break time reversal symmetry. So the goal is to access non-equilibrium physics or dynamics with a nanoscale probe, right? And you want to really, eventually, you want to do real space imaging plus electronic property measurements of a transient phase. Right? That's what you really want to do, okay? So a phase that exists only for some picoseconds, you want to actually be able to measure its electronic properties. We cannot do that today. Okay, so I have zero optics knowledge, zero. So, and we have built this instrument in my lab, and it was really these two people here, Sokjin Bey, my postdoc, and Arjun Raghavan, my student. They spent 5 years building this instrument, 4.5 years. The thing is that neither of them had extensive laser or optics experience. They had to learn everything from scratch. So it's really amazing that they were able to build this, and all the credit for this instrument goes to them. It's a tabletop scanning tunneling microscope because you need to be able to introduce light. So the light goes in through these ports here. This is glass, and the STM is sitting inside. So light goes in through here. This is the table on which we have the lasers and all the optics. The goal, the reason for all this optics is you'll see we use 2 pulses of laser light, and we need to be able to have a fixed time delay between those pulses. And it's the time delay that we control in order to get time resolution. So some of this optics is to get that time delay, okay? All right. So this is what we have right now. This is the range of our energy, right? So this is, we have an EV or more. We can use different lasers to get higher. But the lowest right now we can go to is 80 MeV for excitation. That doesn't mean we cannot probe, as you will see. It's really interesting. We can probe much sub-millivolt energy scales, even though we're exciting the system with 100 or 1 EV light. The important thing, there are a few important things here. The spot diameter. In order to achieve this tiny spot diameter of 10 microns, we had to install lenses inside our ultra-high vacuum chamber. These lenses are very close to the STM tip sample junction. It's a real physical lens. And that lens can be moved up and down, backwards and forwards to be able to focus the light onto the junction. So that's really important to get the fluence that we need. We have enough power to melt the sample and everything around it. Power is not a problem. And then here it is, time resolution. With our system, we can get we can get 70 femtosecond time resolution. And some of it is determined by our pulse width, which is 200 femtoseconds. Lasers are, you can actually manipulate the pulse width to be even smaller, like 50 femtoseconds, in which case we can get even better time resolution than that. Okay, so today I'm going to be talking about 2 completely different classes of materials. The first one is the Kagome class 135 that you've heard a lot about over the last few days. Stephen Wilson gave a great overview. And in this experiment, we used the laser not to get dynamics, not to get time-dependent information. This was the first experiment we did, but used it as a source of excitation. So we excited the system with the laser light and then did the measurement. So we turned off the laser and then did the measurement. That was the first experiment. And you will see what information we were able to get. The second experiment, this is where the time resolution comes in. This is a wild charge density wave system. And it's got lots of interesting physics in terms of topology. However, one of the things that was discovered recently is that the charge density wave, I'll tell you in a bit, of course, you know that a charge density wave, its lowest energy excitations are the phase mode, where the charge density wave can slide. So that's called a phase-on. And also an amplitude mode, where the amplitude of the CDW can go up and down. That's called the amplitude-on. And the phase mode is typically like an acoustic mode. It's like a plasmon, it's an acoustic mode. But in this class of materials, it actually becomes an insulator below the CDW transition. And due to that, there are very few quasiparticles for screening, so the Coulomb interactions are not screened. And because of having strong Coulomb interactions, you can go from having a massless phase mode to a massive phase mode. And this massive phase mode, the way the particles acquire mass, is very similar to the Higgs mechanism. And it was predicted a long time ago, but never measured, actually. And so last year, one of my colleagues, Fahad Mahmood, saw evidence for the existence of this massive phase-on in this compound. And I'll show you what we see with our technique, right? So this phase-on has a frequency of terahertz, and I'll show you what we measure and how we can get additional information through what we're doing. Okay, So let's just start. So this is, we are using now laser light to manipulate the charge density wave state of a Kagome material. So the work was done by my two postdocs, Seokjin Bae and Yuqing Shin. We had a whole bunch of theory help from the group of Rafael Fernandez, who's now actually at University of Illinois. He moved, but he was at Minnesota at that time. And Ziqiang Wang from Boston College. And we got really nice single crystal from Stephen Wilson's group at Santa Barbara. Okay, so time reversal symmetry. We're familiar with one way to break time reversal, and that is to have an ordered set of moments. So if you have, localized spins in your system, and they order in any way, ferromagnetically or even antiferromagnetically, then you break time reversal symmetry. However, there is another way to break time reversal. We're very familiar with this. You know that if you have circulating currents, you can break time reversal symmetry. And however, in the 90s, in the context of the cuprates, Chandra Varma, Haldane, and a bunch of other people proposed that in a material, in a solid state system, you can have a spontaneous generation of currents on a very small length scale, on lattice length scales. So these are called loop currents, or it's also called an orbital moment. So you can have tiny currents generated on atomic length scales in your sample. These tiny currents can generate a small magnetic moment. And if you have a lattice of these little loop currents, then you can also get broken time reversal symmetry. So this is called, this goes by many names: loop current phases, orbital magnetism, flux phase. And so you can see here, this is one example. You could have currents going in this way. This is like a unit cell. You can have currents going this way and then this way. And in this case, of course, there's no net moment. But you can also imagine these being staggered. If they're staggered, then in each loop, you'll have a net moment, okay? As long as there's no net current in your system, this is allowed. So just because it's allowed doesn't mean it happens. And, people have been looking for these loop current phases for a long time. And I'll show you there is some evidence that these new class of materials actually support this kind of loop current phase, which breaks time reversal symmetry. Okay. So the material I'm going to be talking about is this 135 compound, and specifically the rubidium, vanadium, antimony, 135. It's a Kagome system. So you can see this is the Kagome plane right here. You can see it here as well. Right above, you have a honeycomb layer of antimony atoms. And above that, you have a hexagonal layer of alkali atoms. So hexagonal, honeycomb, and Kagome. That's what is stacked. And the thing is that when we cleave, we usually expose this, something like it cleaves here. So half of these alkali atoms leave. So what we usually do is we use the STM tip to remove the rest of them. Right? We remove the other half of the alkali atoms, and then we can expose this surface, which is really close to the Kagome plane. So, I'll quickly run through the phenomenology. So you can see the dates here. This is 2021. So this is a relatively new class of materials that's been discovered. So essentially, μSR shows that there are no local moments. Okay? So there's no reason for the system to be magnetic. However, there's evidence for broken time reversal symmetry. The first evidence for broken time reversal symmetry came from Zahid Hassan's group, who did STM studies. And so this material has a charge density wave order below about 200 Kelvin, okay? And these peaks that you see here are the Fourier transform of a topography in STM. So these are the charge density wave peaks in the Fourier transform. What he showed is that, I think Stephen and Ming talked about this briefly, you can manipulate the intensities, the relative intensities of these charge density wave, using a magnetic field. Okay, so you can see here in this, for +2 field, this is high and this is low. And in a -2 field, it's the opposite. This becomes this, it's high, and then this is low. So you could manipulate the relative intensity using a magnetic field. So think about what this is saying. You have a charge density wave order. There's no spin associated with it. You take a Fourier transform of a topography. You see the Fourier peaks. First, they should all be the same height. There is no real reason for them to be different heights. So the first question you should ask is, why on earth are they different heights in the first place? And the second thing is, there's no reason they should respond to a magnetic field, right? I mean, why should a charge density wave respond to a magnetic field? It's a neutral object, spin-wise, sorry. So that shows that there's some broken time reversal symmetry. They didn't have an explanation for what was going on, but it was the first indication that there might be broken time reversal symmetry. The second is that mu-SR in the presence of a magnetic field show an enhancement of the relaxation rate below the CDW transition. Okay, well, in this, I misspoke. The CDW transition is somewhere around, I thought it was around 100 Kelvin. In any case, there's an increase in the relaxation rate in mu-SR, and this increase indicates, again, that time reversal symmetry is broken. Immediately afterwards, there was a lot of controversy. Different groups started showing different things. The first thing is the original STM experiment by Zahid was not reproduced. There was another group that did measurements and didn't see this kind of magnetic field sensitivity, right? The controversies are irritating, but they also are extremely interesting. Whenever there's a controversy, there's actually usually a reason for all these controversies, and sometimes you're able to figure out what's going on and sometimes not. I believe here I can tell you what's going on. In any case, so conflicting STM data, I'm not showing it here in the interest of time, but also conflicting Kerr effect data. Kerr also measures broken time reversal symmetry. One group sees broken time reversal, another group doesn't. So huge amount of conflict, so there was no consensus on whether time reversal is broken or not. So then here are the questions. If time reversal is not broken, how do you understand the mu-SR data, that increase in the relaxation rate below a certain temperature? How do you reconcile Kerr effect and STM measurements? Different groups are measuring completely different things. And also, what is this intensity of the charge density wave peaks in the Fourier transform in STM data? What does that actually represent? Does the intensity capture the strength of the order parameter, the charge density wave order parameter, right? Does it actually capture the order parameter in a system? That's the question that we would like to answer. Or is the height of this Fourier transform peak an artifact? Maybe it's got something to do with the tip. If you take a material and any random system and you scan it and look, you see atoms, and then you take a Fourier transform, depending upon the tip that you have, the heights of the Bragg peaks, not the CDW, the Bragg peaks in a Fourier transform in STM data can be very different from one another. And that's something to do with the tip. So when that's the case, how do you take the STM height seriously, okay? So these are the questions, and this is where we were when we first started this experiment. You know what this means. Lots of different groups saying lots of different things. Okay, why are we interested in loop currents, just very briefly? Why are they exciting? Not because they're not just because they're an exotic phase, but also if you have loop currents, remember, this material is also a superconductor, so superconductivity would emerge below the CDW TC, which means superconductivity is emerging in the broken time reversal symmetry phase, which indicates that it's possible that superconductivity is exotic in the system, okay? Another thing is that if you have broken time reversal symmetry of the kind I was talking about, where you have these loop currents, then in the superconducting phase, there are predictions that these single particle loop currents would turn into Cooper pair currents, little loops of Cooper pairs, which is a vortex. So you can have a lattice of vortices and anti-vortices in your system. And then there are many other interesting consequences of having loop currents and then superconductivity. So having the loop currents is actually pretty cool, and we'd like to see if this is happening in this system. Okay, so my original idea when I heard about Zahid's experiment was, okay, well, we know we can break time reversal symmetry with circularly polarized light. And so why not shine circularly polarized light on this CDW system as it goes through the transition and see if we can manipulate the order of this charge density wave with circularly polarized light. That was the original idea. It was a spectacular failure. It didn't work, right? My postdoc tried it and they couldn't see anything. It just didn't work. So then they tried linearly polarized light, and that's the data I'm about to show you. Okay, so here's just a schematic. We have the laser, and then we have these two lenses inside the UHV system, and then light comes in, gets focused by these lenses, and here's your sample, here's your tip, and we make measurements using the STM tip. Oh yeah, let me show you. It's here too. Here's something interesting. Remember, the spot size is 10 microns, and your sample is large. So one important thing is here's your spot and here's your tip. You don't want to miss the spot with your tip. You want to be measuring right on where you're shining the laser. And to do that, the other lens is really useful because we can see. What you're seeing here is the tip, STM tip, the sharp thing, and its reflection on the sample. And here's the beam. So this is how we align things. We actually see where the beam is, look at the reflection of the tip on the sample, and make sure that everything is aligned, okay? Okay, yeah, and so, sorry about that. And so what we do is we, find an area, clean it up, use a shine laser light, linearly polarized laser, not circularly polarized, and then turn off the laser, and then measure. That's what this experiment is. Okay, so let me just show you what it looks like. So let me show you the CDW first. This is an image above the charge density wave transition. It's from this paper. And you can see the Bragg peaks. This is, it looks like a hexagon, but because it's the antimony surface. And then you go to low temperatures below the CDW transition. You get additional peaks, 1, 2, 3, 4, 5, 6. They're at a smaller Q, that means larger real space periodicity. This is a 2x2 charge density wave, so the size of the unit cell in real space is just doubling. So every second atom it's bright, dark, bright, dark, bright, dark in 3 directions. That's the charge density wave. So in real space, what happens is you get this sort of trihexagonal charge density wave where all of these atoms shrink a little bit, just a tiny bit, okay? So this ring of atoms just shrinks towards the center, and then this ring of atoms shrinks a little bit towards the center, right? CDW is associated with electron-phonon coupling. Whenever you have a charge density wave, you also have lattice distortion. This is the lattice distortion that you see in the system. All of these atoms basically go a little bit towards the center, so then you have bright, dark, bright, dark. That's what the CDW is. Okay. So here's our data. This is the topography. These are the 6 Bragg peaks, and then right inside are the 6 CDW peaks. And inside is quasi-particle interference. I talked about this yesterday. I'm not going to talk about this at all. I'm going to basically mask the center so you don't see the quasi-particle interference. And I'm just going to basically focus on these 6 charge density wave peaks. And when necessary, I'll show you the Bragg peaks as well. You'll see this is really interesting. So the first, these are the charge density wave peaks. The first is these 1, 2, 3. These are the 3 CDW peaks. They're all different intensities. Now look, the Bragg peaks are also different intensities, and they're not different intensities in the same way. This is tall, this is short, this is medium, this is medium. This is, it's really difficult to say how these two things are correlated. So this is why I'm saying it's really difficult to know what information is contained in the intensity of the charge density wave peak. But in any case, it does tell you, if you take this seriously, that two symmetries are broken. One is rotational symmetry, because this peak and this peak, Q1 and Q3, this peak and this peak, Q1 and Q2, don't have the same intensity. And actually, it's not surprising that one of the three should have a different intensity, because this is a 3D CDW. If you look at one layer, the layer underneath it, the CDW is shifted in one direction, okay? It's staggered, so in an alternating way. So because of that, one direction is picked by the system, so one of the CDWs can be a different intensity. So rotational symmetry is broken, that's okay. The thing is, mirror symmetry is also broken. This peak and this peak are not the same intensity, so that's, a bit surprising. And I'll show you later from our data, we believe that the reason these two are not the same intensity is not anything intrinsic to the sample. It's because the sample is extraordinarily sensitive to strain. The smallest strain in the sample can actually change the intensity of the CDW peaks. Okay. So here's our experiment with the light. So let's just focus on these two charge density wave peaks. What we did was we can control the electric field of the light to point in any direction we wish. And we use that electric field, so we either point it in this direction or this direction. And by pointing the electric field of the light in different directions, you will see we are able to manipulate the intensity of the charge density wave, okay? So this is our starting point. This is taller than this. You can see it here. This is taller than this. And now I shine light in this direction. And now look, this is taller than this, right? See, this is taller than this. You can see there's a reversal. Initially, this was taller than this, and now brighter. This is brighter than this. And now shine light in this direction. This is brighter than this. And now shine light in this direction again, and it reverses. This is brighter than this. Can you see that? Can everybody see that? So by shining light along a certain direction of the charge density wave order, we can make the intensity of the CDW peak higher in that direction. So the question is, what is going on? Why is the CDW peak in a given direction becoming stronger because of a light, okay? So by the way, this is fully robust and 100% controllable. Every single time we shine a light with the electric field pointed in one direction, the CDW in that direction gets stronger. Every single time with 100% fidelity. Okay. So one possible answer to this is that because of the light with the electric field along a direction is exciting phonons in that direction, perhaps the system is finding a new equilibrium phase where the atoms are distorted. I told you CDWs are associated with lattice distortion. So perhaps there's a new phase where the atoms are distorted slightly more, and because the distortion is higher, then the charge density wave is more intense. That's one possible explanation. That would be something like electrostriction. So the question is, can we see this, right? If we could see that the atoms are distorting more in any given direction, when the CDW intensity is higher, it means that this is something real. This is not an artifact of the tip, right? That atomic displacements are real things. So we can measure that. So here are the Bragg peaks, the 6 Bragg peaks, right? The CDWs are very faint. You can see them here, 1, 2, 3, 4, 5, 6. So let's just focus on this Bragg peak and this Bragg peak, these two Bragg peaks. This is QB3, QB1. Before shining light, this is where the Bragg peaks are. When you shine light along Q3, which is this direction, this Bragg peak, you can see the Bragg peak moves. So this CDW will get more intense, and the Bragg peak has shifted closer. the Bragg peak has shifted further away, and therefore the real space distortion is higher. And this one has shifted as well in the opposite direction. And then you apply light along Q1, the Bragg peak shifts back, see, shifted back from here to here. And this one has also shifted. So let me just summarize. What this tells you is that every time the charge density wave intensity gets stronger, what we find is that the lattice distortion in that direction increases, okay? So now we have, and again, this is fully repeatable. This is a sequence of light pulses. As every time the intensity in one direction gets higher, like this is red is higher, there's a distortion. So let's see, this blue is higher. Lattice distortion has gone up in that direction. Then red, that it goes up in that direction. So the lattice follows this charge density wave. Okay, so what the light experiments tell you is that A, of course, there's strong electron-phonon coupling. This could not have been possible without that. B, yeah, the fact that we're able to manipulate the charge density wave intensity with light means that the intensity of the CDW is a real a measure of the order parameter, the relative intensity, okay? The intensity of the CDW by itself, if you didn't do anything to it, you actually don't know what's going on. You don't know what's determining the intensity. However, the relative intensities of the different peaks have physical meaning, okay? So if one is higher than the other, there is some physical meaning embedded in that. The physical meaning is that the lattice distortion is larger in that direction, which means the amplitude of the order parameter is larger in that direction. So that's what our laser studies have told us. Okay, now armed with this knowledge of what the intensities mean, we can then go back and look at the experiments with magnetic field. So we repeated the magnetic field experiments done by Zahid, and we see the same thing they do, meaning that in different directions of magnetic field, perpendicular to the sample, remember. So you're applying a field perpendicular to the sample, and you can actually change the relative intensities of the charge density wave peaks just like he saw. Now the question is, okay, can we show that this is also real by looking at the lattice distortion? And in fact, that's what we see. So what we expect is that when you apply a perpendicular field, you expect that if the intensity goes up, for example, if you apply a field and this intensity goes up, then the lattice, the Fourier transform peaks should also shift correspondingly. That means the lattice has contracted. And there is actually one way to do this, right? It's very difficult to see how a perpendicular field could move things in the XY plane, right? How can you apply a field in the Z direction and have motion in the XY plane? And one way to do this is by a mechanism called piezomagnetism. Piezomagnetism is exactly this. You apply a field in one direction, and you have a response in the perpendicular direction. So then we, of course, check that. This is the Bragg ratio, and just like with the laser light, every time the charge density wave intensity is high in one direction, you get a corresponding distortion in the same direction. Okay, so that's all I want to say. So we did a combination of light and magnetic field studies. And with this combination, we were able to show that the charge density wave intensity actually encodes real information on the strength of the order parameter in a particular direction, and that this CDW intensity can indeed be manipulated with a magnetic field. And we proved that that's a real thing by looking at these lattice distortions that are accompanying the CDW intensities. And then we worked with our collaborators to, it's in this paper, so I don't want to go too far into it because I want to tell you about the dynamics. But then what really is happening in the system is that there are two kinds of orders There's a bond order that Stephen Wilson was telling you about in the 3 different directions. That's this one, right? And that's you can think of as the regular CDW order. There's also a loop current order. Here you have spontaneous loop currents going in 3 different directions. So for example, this would be one of the order parameters. Here you have currents going this way, this way, this way, this way. Then you have the second order parameters, current going this way, this way, this way, this way. And then the third order parameter, 3 loop currents, right? They don't look loopy. They're going in one direction, but they're still currents. Any spontaneous current means broken time reversal symmetry. So now, Rafael showed using a very simple, some symmetry analysis that using all the constraints from our experiments, this is the kind of order you expect in the system. You have this loop current order, up, down, up, down. It's like an antiferromagnet. Okay, so how does this resolve any of the controversies? Let me just cut to the chase. Essentially, what we believe is happening is that all the experiments are measuring real things. The controversy arises because of the differences in the amount of strain in the sample. From our experiments with the magnetic field, we can see that this system, if you have shear strain, you'll get a net moment in the system, okay? So that can explain why different Kerr effect data see either broken time reversal or no broken time reversal. If you had no strain, the kind of order that we are talking about with the loop currents, that will not give you Kerr effect. So there should be no Kerr effect. So same with the STM. If you happen to have a particularly strained sample, we actually do see this ourselves. You will not see this reversal with a magnetic field. So the sample is extremely susceptible to strain, and time reversal symmetry is indeed broken. Okay, so that's it for the first part of the talk. Shall I just keep going? Yes? Yeah.
Yeah, my question is about the redistribution. Thank you. The redistribution of the peaks that you get when you flip or switch the sign of the magnetic field. Do you do that in like sharp steps, or can you look at how the transition goes from one?
Yeah.
Is it smooth, or is there some switching?
We have not done it, actually. It's a really good question. In fact, there's another associated question, which is what happens at zero field, right? Let's say you go to 2 Tesla and you have some order of the intensities. Then if you go back to 0, then what happens? Does it keep that order, or does it switch it? And the thing is, we didn't do all of these experiments. We haven't done them yet. We intend to do them. So go slowly from 0 to 2, see what happens, or even go higher, see what happens. What happens at 0? Is there hysteresis, which I suspect is there, and that's another thing we could figure out by doing what you're saying. I don't know. Piezomagnetism might imply that there's some threshold. It might also imply it's continuous. I don't know. There might be if there is strain in the sample, which there is, that is why the 2 mirror symmetric peaks don't have equal intensity. It might require a certain amount of magnetic field before the intensities can be flipped. So yeah, I don't know the answer. It's a very good experiment to do.
Thank you.
So that I got it right, that if you would have a system with absolutely no strain,
yeah.
then you don't see this time reversal.
No. The time reversal symmetry would exist no matter what. A broken time reversal symmetry. So the system has loop currents. Okay, let's start there. It's a really good question. So the question is, if there were no strain, would you still have loop currents? The answer is yes. All I'm saying is that if you looked at a system with no strain, and the staggering that I'm talking about in 3 dimensions, let's even say that was not there, then in theory, all the CDW peaks should be the same intensity. However, in a magnetic field, you would still see the piezomagnetism. So in a magnetic field, suddenly the relative intensities of the peaks would be different. And then when you flip the peaks, you would flip that because of this piezomagnetism.
So you are saying that this genuine effects
The combination of strain and broken time reversal symmetry can create confusion. However, the fact that the system responds to magnetic field at all tells you that time reversal for this particular sample, if you do the analysis, time reversal symmetry has to be broken because there are no local moments, and the only way of getting such a piezomagnetic response is through broken time reversal symmetry.
According to you, then, that the piezomagnetic response is due to the loop current. So
Yes.
without loop current, you wouldn't get any piezomagnetic.
Correct. Absolutely, yeah. That's correct.
Is there a simple reason why the charge density wave order is coupled to the loop currents?
That's a great question, and I don't think they're necessarily coupled. So this particular sample has only one CDW transition, whereas there are other samples of the same family, 135 family, where there might be, these two might have different, that's another experiment we'd like to do, they might have different transition temperatures. So it might be that, because what they see is that the broken time reversal symmetry is happening at a different temperature from the charge density wave temperature. So it might be that the bond order sets in first, and then the loop current order sets in at a different temperature below that. Yeah, so there's no real, I don't know if there's a reason. The one reason I can think of is the CDW breaks the same symmetries as the loop current. So perhaps that might explain why they occur at the same temperature in this sample.
Okay, thank you.
That's the thing. I think some 100-something degrees. I've actually forgotten.
This might be a stupid question, but can they do anomalous Hall experiment and see if time reversal is broken? Because that could be.
So this kind of ordering, I believe, it's not a stupid question. It's a good question. This kind of ordering, I believe, it would not. I'm not sure if it'll give you anomalous Hall. It's like an antiferromagnet. Perhaps it can. The one issue I do have is these loop currents are tiny, very, very small. For example, neutron scattering will not be able to see these, as far as I know. So I'm not sure, even if there were a signal, how big the signal would be. But there are experiments done by Philip Moll, who's done some very careful experiments where he takes the same samples, makes sure there's no strain at all, measures magnetotransport, and then strains the sample, and then measures magnetotransport, and shows that magnetotransport is affected by strain. So that's another sort of experiment that actually corroborates this idea.
I think I have a silly question maybe, but so you're discussing this in paradigm of lattice distortion, like when you apply electric field, like oscillating. But then do you consider contribution to electrons? I mean, do you consider how the single particle band structure could change?
With the light?
Yes, with the light.
Okay, but here's the deal. That is a good question, but here's the deal. The way we did these experiments is we turn on the light, and then we turn it off. And so it's a pulsed laser light, so even like just one pulse or two pulses, just 1, 2, right? Remember, these are femtosecond pulses, just on and off. And its light is off. Mm-hmm. So then while we're doing the measurements, the light is off. So as a driving force for changing the CDW intensity, I don't know. Electron phonon coupling seems to be the best bet.
Okay, thank you.
Okay, so should I go forward? I have at least 10 minutes. Okay, ask your questions, and then please, I have 10 minutes worth of...
Sorry, one question. Then according to you, in the complete absence of strain of fields, you recover the 6-fold symmetry.
Say that in the absence of strain.
Or magnetic or electric fields, which then you recover the six-fold symmetry.
Without the staggering. So this material has the staggered CDW, so that picks one direction out of the three. So you don't fully recover rotational symmetry, but you should have mirror symmetry, yes.
Okay.
But this particular sample, you won't get the rotational symmetry back. But in other samples, without the staggering of the charge density wave, you will recover your six-fold symmetry.
Okay.
Excuse me, can you go back to the slides one before the summary one?
This one?
No, former. Before summary one.
Before summary one. Oh, you mean the this one?
Yeah. Also, this figure is fine.
Yeah.
Maybe I didn't understand this panel correctly, but I found the left panel and right panel doesn't match in the magnitude.
Oh yeah. So even with the light, the amplitude of the effect is nothing. It's not something we can control. But one thing I have to say is that so this already tells you there might be some inherent strain in the system. So the amplitudes never match. But there's the one I'll tell you this is the reason why this is so important. These intensities, STM people usually don't take these intensities seriously unless you can manipulate them, because there's always some tip effect. Let's say you turn on the field and something changes. How do you know your tip hasn't changed? That is why this is so important. This gives credence to this. The Bragg peak distortion, that is real. That is not a tip effect. So then when this and this go hand in hand, you know something real is happening.
Okay, I see.
Okay, so please feel free to ask me questions in the break. In the next remaining 8 minutes or so, I will quickly go through how we can get time resolution with our system. So this is basically food for thought, okay? That's what it is. Okay. Again, these marvelous people, Sokjin and Arjun, built this beautiful instrument and got this amazing data. We got samples from Daniel Shoemaker's group, and we're working with Barry and Ziqiang for theory support to help us understand what's going on. We don't fully understand what's going on in the system. It's a charged wild charge density wave material, tantalum selenium iodide. While in the sense that above the CDW transition, it's a wild system. It has broken inversion symmetry, and that's why you have these wild cones instead of Dirac cones. So the system has very little symmetry. Just to start with, I have to tell you that. The second thing is the charge density wave is a very interesting charge density wave. It's a long wavelength, incommensurate 1D charge density wave. That's the CDW I'm talking about. Okay, so if you have a charge density wave, here's your CDW in 1D, then you can have two different kinds of excitations, right? One is you can have the amplitude go up and down. In fact, you saw examples of that in the previous talk, the amplitude of the CDW changing with light. The other is that the phase of the CDW can slide. So both of these are low energy excitations. This is called the amplitude on, and this is called the phase on. The phase on is usually behaves like sound. It behaves like an acoustic wave, a massless acoustic wave. And the amplitude on can have a mass because there's some energy required for this. But in a normal material, a charge density wave is pinned by impurities, so it can't slide that easily. So think about an incommensurate charge density wave. What prevents it? What tells you where it's supposed to be, where the wave is supposed to be? Nothing. It's a broken symmetry, right? It's just choosing to be here. It might as well be here. That's your phase of the CDW. But But in a real material, the phase can be pinned by impurities. So if you want to move this charge density wave, slide the phase, you have to actually apply a little bit of force, okay? And so that gives the phazon a tiny bit of mass, but usually it's not a big amount of mass. So you have this, in general, you have this, this is omega versus k, this is dispersion. You have this massless phase mode, and then you have the massive amplitude mode. That's the usual charge density wave. This is just folded to 0 because you have whenever you have a CDW, you have a new Brillouin zone, and so you see everything that happens at the CDWQ, you see at the gamma point. Okay, and this is also important because then that's how you couple light to it. Now, in 1973 and 78, Lee Fukuyama, Lee, Rice Anderson, they wrote a couple of papers, in fact, there were more than 2, that showed that when you have poorly screened Coulomb interactions in a system, so remember, CDWs usually occur in metals where screening is really good. However, if you have a CDW in an insulator, right, the CDW actually gaps out your entire Fermi surface, then you can have very poor screening. Or for some reason, if your density of states is very low, you can have poor screening and therefore a large long-range Coulomb interactions. And if this happens, then your massless acoustic phase mode can acquire a mass that's even larger, so it can go from here to here. So your phazon can acquire a pretty large mass. And the mechanism by which this happens is, like I said, similar to the Anderson-Higgs mechanism for giving mass to massless particles. So this was first observed just last year by my colleague Fahad Mahmood in the same sample I'm talking about. What they did was they applied light, optical pulses to a sample, and in their measurement, they measured the emitted terahertz. Okay, so now I'm running slow. It's 9:58. Can I have 10 more minutes? I don't think Andre is here. Is Andre here? Oh. We'll just pretend he didn't say that. So let me just take 10 more minutes and then finish this. Yes, he is. He's hiding. Okay.
I think, to be fair, because yesterday, I myself stopped exactly at 10 and there were questions, so 2 minutes more of talking and then the questions.
Okay, well, I won't be able to finish in 2 minutes, so I'll take 5 minutes. Okay.
And less questions.
Okay. What they did was they put in optical pulses and measured emitted terahertz, okay? So remember, these are emitted terahertz. So terahertz light is being emitted when the system has optical pulses incident on it. And this is the terahertz field they measure, and then you take a Fourier transform, and you see this strong terahertz oscillation at 0.22 terahertz. That's what they saw. Remember, that's a very small energy scale. And then what they did is they tracked the intensity of the terahertz emission, right, as a function of temperature, and they find that at a temperature of 0.3 Tc, suddenly the amplitude of this terahertz oscillation emission increases. And this 0.3 Tc is something that's predicted by these people and suggests the existence of this massive phazon in the sample. And because the sample is an insulator, it actually makes sense that the phase mode should become massive. So we decided to do this experiment with our new STM setup. We did 2 kinds of experiments with the same setup. One is pump probe reflectivity, and the other is measurements. First, I'll show you point contact, and then very briefly, I'll show you tunnel current measurements. So current measurements as well as reflectivity. So this is the heart of our system. So if you understand this, you understand how time resolution works. So the way it works is the following. You send in 1 laser pulse. The system gets excited, okay? And then you send in, with a time delay, you send in a second laser pulse. And then the response of the system to the second laser pulse depends on the time difference between the first pulse and the second pulse. Because just in a very simplistic sense, imagine the system is excited by the first pulse, and then the second pulse comes in immediately, then it's not going to excite the system that very much, okay? However, if the second pulse comes in after a long time, the system's going to get excited all over again, okay? So the time resolution in our STM studies and in the reflectivity studies that we did, it all comes from manipulating the time delay between the two pulses. And this time delay can be manipulated on femtosecond timescales. This is how we get time resolution. Okay, so what we do is we measure two things. One is the reflectivity as a function of this time delay in real time. So the delay will be like, in this case, some femtosecond. As you change the delay, you measure the reflectivity in real time. And then you also measure either point contact or STM current in real time as a function of this time delay. And remember, the current that we are measuring is average current. It's not that part of the measurement has no time in it. The only time in this whole measurement comes from manipulating the delay time. Okay? All right, so let's see some data. This is the optical pump probe reflectivity, and this is the point contact, and I'll show you our STM data looks the same. And you can see the reflectance has oscillations on picosecond timescales. The point contact current has oscillations on picosecond timescales. And if you take a Fourier transform, you will see what I want to show you. But first, let me show you very quickly. We don't have time. This is the material. You see these stripes? That's the charge density wave. You can see it's a very long wavelength. Here are the CDW peaks, and here are the Bragg peaks. Okay, so now let me actually show you the data. Here's the pump probe reflectivity. Here's the Fourier transform. Oops, here's the Fourier transform. You can see two peaks, one at 0.22. This is seen as terahertz emission in Fahad's data. But we also see one at exactly half at 0.11. And these intensities are a function of temperature. If you plot the intensity of the peaks, so here's Fahad's data. This is 0.3 TC. The terahertz emission suddenly goes up, evidence for a massive phase-on. When you look at reflectivity, that does not happen. These modes, the intensity actually goes down at exactly that temperature. Now let's look at what we measure with this either point contact or STM. We see the same oscillations. Here are the two peaks again. First, this is a miracle, okay? It's amazing. We have less than a picosecond time resolution in order to get frequencies of 0.11 and 0.22 terahertz. You should be amazed by this. And again, but then now you do temperature dependence, and the temperature dependence of both of these peaks falls exactly on Fahad's data. So the reflectivity and the point contact or the tunnel current measurements show completely different temperature dependencies. So in any case, I think this is tunnel current data. You see the same peaks. Okay, I'm going to actually stop here. So this is our data right now. We've measured, using the pump probe technique that I talked about, both reflectivity and point contact by measuring in real time and then taking Fourier transform and looking for peaks. The reflectivity peaks, there are two of them, 0.11 and 0.22. By the way, Fahad's technique cannot see these 0.11 peaks because they don't have sensitivity at these frequencies. So perhaps what they identified as the 0.22 phase-on might just be a second harmonic of the 0.11 phase-on that we are seeing. However, maybe it's something else. We don't know. We don't actually know how to identify these two modes. Interestingly, there's some sort of competition. This looks like we're measuring phonons, whose intensity is going down, while the intensity of the phase-on is going up. They're one entity, right? The phonon and the phase-on. So we don't understand this data. If you have any ideas, let me know. Thank you for your attention.
Sorry, is there any magnetic ordering in these experiments?
No,
Okay.
only broken inversion.
Okay, thank you.
Okay, I don't say immediate questions, so we can move on. So Andre can come here and next time.
Thanks.